Hello, everyone. Thank you for coming to the ABI Zoominar today. We have two speakers, Dr. Huidong Bai and Dr. Amit Badi, all research fellows at the Empathic Computing Laboratory established within the ABI. First, Huidong's research area includes exploring remote collaborative mixed reality interfaces. And Amit has a background in arts, and his research interests lie at the intersection of the arts and science and engineering. So today it'll be really interesting to see what these guys have been researching, and so they will be sharing the latest research that's being carried out at the Empathic Computing Lab to enhance human interactions in virtual spaces. So over to you, Huidong, first.
Thank you, Vicky. Let me share the screen now. Can you see the screen?
Yep.
Cool, thanks. So hi, everyone. Good afternoon. My name is Huidong Bai, and today I'll talk with my colleague Amit together about the how we use AR/VR technology to bridge and merge the reality and the digital world together. And we both work at the Empathic Computing Lab at the Auckland Bioengineering Institute. Great. So I'll take the first part, Tele-existence, or normally I would consider the fundamental of this question is how we built the communication for remote people. So as we know, the Zoom is quite a big thing these days for all of us. Currently we're stuck in Zoom as well. Zoom is really powerful tool that connect people remotely efficiently, but also on the other side, it has limitations. It's just a face-to-face, it's just a teleconference software and can provide the camera feed with each other. And but the reality that when we think about the face-to-face communication, there are lots of cues happens at the same time. For example, when you have the group discussion about the project idea, you normally, of course, had the audible cues. You describe the idea. At the same time, you also had the visual cues. For example, the gaze, eye gaze, hand gesture, face expression, and body pose. On top of that, we also have the environmental information as well. For example, the environment you are surrounded, or the 3D model, like mock-up model on the inside the picture. It's a target object that you will try to present. These objects or environment have the special information in 3D. So you need to, for the speaker or presenter, you need to understand the spatial awareness. And also, for example, the occlusion, the depth perception, all these could be included inside the face-to-face communication. But if you think about the Zoom, actually this was not provided. Especially because of the COVID, everything changed these days. Lots of travel ban, and there are lots of, most of the people work from home, and we try to adapt this new normal these days. What we are trying to do at the ECL is trying to enhance the mutual communication with AR/VR technologies. So our specific research area is a remote collaboration or tele-existence. So Zoom is one specific office communication tool, but if you go beyond the Zoom or office scenario, it's a more complicated real scenario or application that we need to deal with. This is one really rough idea, a common idea that we try to handle with. For example, on the local side, the worker tried to fix a problem, but he has no enough knowledge or experience or tools, experience to solve the problem. So he used sensor cameras or different cameras, sensors to capture the local environment, share the information to the remote expert who has enough knowledge or methods to solve the problem. So the remote expert receive this information, analyze that, and give the feedback based on these problems. So the solution of the guidance will be fed back to the local people through different technologies and help guide or help the local worker to fix a problem. So this is the overall idea or scenario they want to address with our technology. But what kind of technology we can use? Well, if you check in the past few decades, a different technology has been explored, mainly from two perspectives. First is how we share the view of the local environment. Second, how we enhance or share the communication cues that we have. And with all these two information, we try to simulate or provide similar experience like face-to-face communication. And of course, if from the left hand, there will be the audio, which is common for everyone, and still image used with a smartphone with mobile cameras equipped. So you can capture the image, give the annotation, send to the partner, and the partner will give the annotation, set it back, show where you want to solve the problem. Especially in industry, this is really helpful. But still, it's static image. It's outdated. It does not provide live information to the scenario. So we also use a live video like the Zoom on Skype or the other similar tools that we can use to build the conversation in real time, solve problem more efficiently. And on top of that, there are quite a few companies use the 360 camera to capture the live 360 image or video and share with the remote user partner. It can also give the better awareness of the situation. And later, the 3D with the RGBD sensor, we can also build the 3D environment of the local. But how could we bring these new technologies, especially 360 and 3D, into the teleconference that we have these days, like the Zoom? So the first system or the first project that we built is the 360 Tele-existence. And consider the scenario of the tourism. Nowadays, because of COVID, there are very limited international people travel to New Zealand to enjoy the amazing view and spots in New Zealand. Could we use this technology, extend the Zoom and use this technology to attract these people and provide kind of similar experience that they had if they can visit New Zealand? So this is one example that I will show. As you can see, at the first beginning, it looks like normal, the Zoom-like system, just a basic conversation. But if you go back to the right side, we talked with Johnny. Actually, on his side, he had the 360 camera and it's interactive and live at the same time. You can rotate around without asking Johnny's permission, but that could be really helpful in the on the industry side or tourism. At the same time, we can give a higher resolution 4K pre-recorded video. Then this could be used for a tutorial on the site or give the pre-recorded dedicated site information. At the same time, we can go up to 8K still image. And of course, because it's still image, so we can teleport to different sites. After finish this, we can go back to the normal live video that we have, but it's interactive. On top of that, we still, with the 360, it's still 2D 360, right? And for some tasks like the design course or the lecture for the architecture, they always try to present the 3D information, 3D model in real time. Before the COVID, before lockdown, they have this mock-up model can present to the student, but now they can't because of the 2D limitation of the Zoom-like system. And what we can do is to bring the VR system into the Zoom and achieve this kind of experience. On top left, you can see that Pushan is now wearing the VR headset and immerse himself in the VR environment. But his virtual camera feed can fit into the Zoom system, Zoom-like system, and show around in 3D space. At the same time, other users can also join as a group. So here, Prashant pick up the 3D model, and can also see the Zoom 2D interface as well. And to introduce the architecture design, he can walk around with his friend. And also, if he want to do more dedicated, detailed explanation, he can use a drawing on the whiteboard, and that will give much more immersive and detailed 3D information rather than just a purely 2D. If you check the path or the evolution of this information sharing technology, we talked about 360 2D and 3D VR, but what's next? How could we predict the future of this trend? So from our research or our understanding, the future will be the 360 3D live sharing. It's 360 and it's 3D and it's live. It's combine all the advantage of the past technology, but go beyond. So we start to investigate that 360 3D tele-existence technology, and consider this could be used for the equipment maintenance in the factory, for the server installation, and new machine installation as well. Lots of applications can be used. But first, we need to solve the problem of the capturing. How could it be a sensor? Because we cannot use the 360 camera to capture 3D, and we cannot use one RGBD sensor to capture the 360 depth information. So our solution is to build a RGBD depth cluster that can stitch 8 or more than 8 depth images at the same time and calibrate them and feed into the computer to generate these 360 3D environment image. And it can also be live. Then share this to the remote user through the network and render on the remote side, either on the computer display or in the VR headset. So this is an early prototype that we achieved. So you can see it's 360. It captures all the surroundings, but it's also in 3D. You can zoom in, zoom out, rotate in 3D space. And everything is live. So actually you can see a person will walk into the scene and just check. Oh, this is the person like walking to the scene. You can see it's all live 360 3D. So we basically achieve the target. We want to build the 360 3D, but you see the limitation of the depth cluster that we have. Because of hardware limitation, the resolution of the depth information is not so accurate or not so detailed in detail. So, but if you compare the normal 2D 360 camera, it can achieve 4K or 8K. So our idea is, could we combine both of these technologies together and provide the compensate with each other? So this is the normal 2D, but it can, after calibration, we can switch to the 3D in real time, and everything is live well. Cool. So once we finish the system, we're thinking we just talked about the first part of the how to share the information of the view of the local environment. But how about the second part, the communication cues? How could we feed the remote experts guidance back to the local worker efficiently, naturally as well, like face-to-face communication? So we conduct the study, build a system on top of the previous one, and conduct study and publish the research paper in the CHI conference earlier this year. So idea is that we use a capture system to capture environment, stream to the VR headset, and the VR headset is equipped with the eye tracker and hand detector. Then capture the remote experts, the experts' eye gaze and hand gesture, and feed that back to the local worker who wear the AR headset and can see the remote ghost hand from the remote expert. So it will look like this. On the left side is the AR view of the local worker. And on the right side is the VR view of the remote expert. So they try to solve the puzzle problem together. They are located physically separated from each other, but they merged in the VR system like side by side in real time in 3D. So you can see on left side, the AR ghost hand is guiding the local person. Now we basically achieve this face-to-face experience. But one thing that we didn't discuss in this whole system or whole scenario is that if we want to achieve the closed loop, one unstable factor is the human being, right? The machine can be reliable, but the human being, he may feel tired physically, or he may be emotionally depressed. So he might not be the best status. So how could we solve this problem? So, well, there's two solutions. The first is to replace the human being with the robot, right? So we start to investigate how could we use the robot to replace the human being and achieve the tele operation. So we just finished this system and did the user study before the lockdown and had the publication done this week. So idea really simple. Instead of using the AR, the local person with the AR headset, we replace the AR person with the robot arm. So on on the top corner is the robot with the sensor surrounded. And you can see on the small corner of the left, the VR person operator tried to operate the robot remotely. So we capture the environment in 3D, feed to the VR person in VR headset, and the VR person is the VR controller to operate the robot in the VR scene remotely. So this all captured in real time. But there's lots of research questions that on top of this. For example, of course, first is how the accuracy of the performance, right? Second is that if we can jump, how could we change the perspective view of the remote person? For example, he can be the robot view, just the first person view of the robot, or he can be the third person view, walking around the robot like the video show and rotate move the robot arm. So he can achieve this kind of remote collaboration with the local person. And the second solution is that if we use some technology, empathic computing technology, to measure the status, emotion status, or physical or psychological status of the local people, and consider as one component of the whole system. So we actually can provide adapted instruction from the remote person. Say, for example, the local worker feel really tired or stressful. At this moment, if we have some technology can indicate the VR remote expert, say the local person is tired now, probably it's not a good idea for ask him to flip this most important switch to turn all the machine down, right? So he can, okay, I should stop and take a rest and then continue. So this part will mainly talk about the brain-computer interaction and also the empathic computing. I'll hand over to Amit with more information. So if any questions, or you can ask later, or if you are interested in any project that we discussed or collaboration, just reach to me through the email here. Thank you very much.
Cool. So thanks, Weidong, for the introduction. So just a second. So before we just go move further a little bit, let's backpedal So these are what you see on the screen. There are essentially the overarching goals that inform the work at the Empathic Computing Laboratory. So right at the top, you'll see the enabling seamless collaboration between individuals in virtual environments. And this is something Huidong has already covered in some detail. Our research also explores how we can facilitate natural interactions between users in these environments. We're exploring interaction strategies that attempt to blend natural interactions with those that afford increased task efficiency. And finally, helping people understand one another is probably one of the harder and possibly ambiguous sounding goals that we have. How are we attempting to help people better understand one another in these collaborative virtual environments that they've already started working in? A part of the answer, of course, lies in our name. We are, after all, the Empathic Computing Laboratory. And so the aim is to develop systems that create understanding, or in short, empathy. What is empathy? It is, as Adler has been quoted, seeing with the eyes of another, hearing with the ears of another, and feeling with the heart of another. So, for the most part, the first two, that is, seeing and hearing, can be considered problems that we have solved or maybe partly solved. As Huidong has already gone through, we can now use 360-degree cameras or stereoscopic cameras to transmit what is essentially a person's POV. And the introduction of binaural sound reproduction means we can mimic a natural auditory perception. But how can we let one another know how we feel in these environments? We do this in the real world via face-to-face interactions that include the exchange of explicit as well as implicit communication cues. And a mixture of these cues generally gives us a good idea of the person's mental state or the mood they could possibly be in. For example, if a person you're talking to appears to be fidgety or their eyes keep moving away during a conversation you're having with them, one could assume that the person is nervous or mentally preoccupied with something else. This assumption, or what is more commonly referred to as a feeling that you get, is based significantly on the implicit and explicit cues that one picks up during such interactions. In the virtual world, one may not be able to convey these cues, but be that implicit or explicit in any manner. So, for example, the image on the left shows how our social interactions for the majority of this year have been. And on the right of the screen is an image that is a screen grab from AltSpace VR. And AltSpace VR is a VR-based world that allows you to interact with people by putting on a VR headset, or it can also be used on a desktop PC. In both cases, you'll notice, or more than notice, I think you would have experienced this now over the last few months, that there is a limited ability to convey either implicit or explicit communication cues. The best form of communication in such situations seems to be our voice. So, what do we do in situations where even immersive environments fall short in being able to facilitate a natural face to face interaction and help us understand one another better? Of course, we use physiological sensors, but why should we use physiological sensors? Research in the use of physiological sensors has already demonstrated that there is significant advantage in providing biofeedback to one or more users in a collaborative virtual environment. Our own work in this domain demonstrates that sharing heart rate between an observer and a participant in a VR scenario significantly affects the experience of the person with whom the heart rate is being shared. So this provides some evidence that physiological sensors can augment interaction in virtual environments by providing feedback of the participant's physiological activity. Some of us already use physiological sensors in the form of smartwatches that tell us things like our heart rate and how we're breathing. The newer ones also inform us whether we are stressed or not based on these parameters. But what if we could use more than just one physiological sensor? Work is underway at our lab to integrate multiple physiological sensors in order to help us communicate with and understand each other better when interacting in virtual environments. For the sake of this presentation, I'm going to limit my coverage of the research with physiological sensors to the EEG device. Almost, as most of you here already know, an EEG device is used to monitor neural activity by placing a set of electrodes on the scalp. So why do we want to use an EEG device? Given that the brain serves as the center for processing all incoming and outgoing information, and that it is the seat of information, it seems logical that we monitor the brain in an attempt to classify our mental states and or emotions among other things. Researchers have shown with some degree of success that it is possible to monitor neural activity to determine mental states. However, more commonly, the EEG has been used as a brain-computer interface. This means that the EEG can be used as an intermediary between the humans and the computer. That is, it can help us humans communicate with the computer. So how does the EEG figure in a collaborative virtual environment? We are using a technique called hyperscanning to monitor neural activity in collaborative virtual environments. For those of you who don't know what hyperscanning is, it is a technique for monitoring or recording neural activity of two or more people simultaneously. So why should we use hyperscanning? Up until now, hyperscanning has been used to study the concept of interbrain synchrony in the real world. So for example, in the experiment depicted by the image that you see on the right, hyperscanning was used to demonstrate that the two individuals who belonged to the same team showed very similar neural activities. So these kinds of studies have reinforced the concepts of flow and connectedness that people playing team sports or other team-based activities with common goals report. Uh, we have begun exploring the use of this technique in virtual environments. And to the best of our knowledge, this is something that hasn't been done before. So the motivation for doing this is twofold. We can run the same or similar scenarios in the real world and collaborative virtual environments to see if we can elicit similar levels of interbrain synchrony in both environments. And this allows us to make direct comparisons between these two environments. Secondly, we'd like to explore techniques that can establish and or hasten the onset of interbrain synchrony among participants in a virtual environment. This primarily stems from the fact that we have the ability to change visual perspectives in virtual environments. And we believe that this can be used to our advantage when it comes to eliciting interbrain synchrony in a virtual environment. An added incentive and something that Hui Dong has covered as well is also to help participants in see if others in a virtual environment are in sync with them or not. So from an application standpoint, this would be useful in a virtual training scenario where the trainer can observe if any of the trainees or participants are in sync with him or her during an ongoing training session. And this would indicate to the trainer that they are engaged in the training session. So some of the preliminary results from our studies demonstrate that hyperscanning in the virtual environments is, we're seeing similar results to those seen in the real world. And in this case, you'll see that a further refinement of the results show that in the real world scenario, interbrain synchrony is observed in the beta and theta bands, while in the virtual environment, it is observed in the alpha bands. And this is right now, we're still trying to figure out why we're seeing interbrain synchrony in different bands across the two environments. And hopefully we will be able to answer this question in the coming months. So I've just covered a very, very small portion of the work that we're undertaking at the lab over here to try and bridge the real and virtual divide and and enhance interactions in virtual environments. So thank you for listening to us. And before I'm going to try and answer your questions, but before that, I'd just like to let people here know that we have 2 masters by research scholarships available in being able to develop and integrate fabric electrodes into head-mounted displays. So if anyone here is interested, or if you know someone who might be interested, please get in touch with either Mark or myself. And the duration of the master's is 1 year, and we have scholarships for domestic students that cover tuition fees and provide a stipend. Thank you.
Thank you. Thank you, Amit, for the presentation. So anybody has questions for we don't have Amit? You can either post your question over the chat box, or you can just unmute yourself and ask a question. I'll go like to presentation. So let's test.
Is there something wrong with the audio?
Can you hear me? I can hear you well.
Yeah, I can hear you.
Yeah. Okay. I have some questions. First of all, we don't very interesting technology. One of the most frustrating things for me, at least in the Zoom or video conferencing, is that the audio delay. But is your advanced 3D technology enhance that side of the teleconferencing, or is it going to be bottleneck with the speed of the internet will always a bottleneck to be able to use that, because the bandwidth requirement will be a lot higher, right?
Vicky, I cannot hear you well. I think your microphone is some problem.
Really? Just
Can you react? Wait.
Can you hear me now? We can hear you, but it's breaking up. Yeah, it's really. Yeah.
How about now? Is it better?
No.
Not really.
Not really. Okay.
Well, you can type out the question though.
Yeah. So I'll type. Oh, there is. I think there is another. Oh, my audio sounds like a robot. Okay. Maybe I'll use my phones. So, anybody else has a question in the meantime? So, is it better?
Yes, good now.
So my question for Huidong was one of the most frustrating for this teleconferencing is the audio delay because of the bandwidth requirement is so high. But wouldn't your advanced technology will make it in terms of those bandwidth requirement? Is it going to be huge increase in bandwidth requirement if we incorporate those 3D captured images and immersed experience? What if so, then what's your tactic to overcome that?
Thanks. That's a really good question, actually. I didn't discuss in details, but there are 2 ways of the solution. Firstly, from design perspective, for sure, if you stream the, like, say, 8K high resolution 360, the bandwidth will be much higher than the normal the Zoom-like system. And one way we can do is that from design perspective, the solution is that we pre-record or preload this information on the server, like the pre-record video or 8K image. That's why we can do that, because we pre-record and upload that, and the user only need to download once. There's no streaming, right? So the second part is technology part. For the especially for the 360 3D, basically you can consider 8 cameras streaming 3 times the information at the same time that the normal 1 camera. So the bandwidth will be really high, but technically we'll do one important thing, that data compression. So we'll do the data compression first, and normally based on our test, currently we can go around 11% original size, but keep the lossless quality of the 3D point cloud. We test the streaming from New Zealand to Italy, and it works pretty well with no delay. And the second is that how we render all these point clouds. If you directly locally render the point cloud and stream the point cloud out by compressing, that might be difficult, because you need to, all the current system, they only deal with 2D image, right? 2D frame. But what we did is that we stream the 2D image first, compress that, stream that, use the current network that we have. And on the client side, we decode that and then do the rendering with the local machine's power. So kind of decouple the computing and split the burden from both sides. So that's achieved. And ideally, later this year, we also test the use Wi-Fi 6 internally inside the lab. That works pretty smooth. But in the future, hopefully next year, we can go with the 5G, far more than we required.
Yep.
So,
okay.
Yeah. So that's our current solution situation.
Okay. Okay. Thank you. So I also have a question for Amit. It's great to see that you are incorporating the sensors into this teleconferencing system so that we can share our emotions or our thoughts like that. But sometimes we don't want to share our emotion. Sometimes we want to hide it. So are you going to incorporate that kind of function? Like, because we don't want to show everything, right?
Yeah, but
But if you wear that kind of EEG thing, it's kind of shown too explicitly to everybody.
Yeah, I think right now, number one, I think I should make it very clear that we're still nowhere near being able to tell things like emotion, because it is so complex. So one of the things that, of course, we're trying is to incorporate multiple physiological sensors to be able to tell things like emotion, cognitive load. But to answer your question, we probably, from an application standpoint, yes, what you're saying is completely correct. Even I don't want people to at all times know what I'm thinking or feeling or whatever it is.
Yeah.
But I think right now, I think like what Huidong pointed out, it will be more of a enterprise-based or enterprise-focused solution where you're equipping people who are geographically separated but need to work together on something for a common outcome. So like in Huidong's case, like with the example of the factory, a remote expert sitting somewhere across the globe needs to inform someone or train someone to do something. And we all know that, if like, for example, if you've taught classes, then you see some students dozing off or not paying attention. So with a device like this, a trainer could sort of see that people are disengaged and then dynamically dial the complexity of the content that is being delivered up or down in order to make sure that time is not being wasted on delivering the content that he or she is, and someone not not understanding it. So that is, I think, so from right now we're thinking of it from a more enterprise standpoint. And of course, like there's another thing that I didn't cover with the hyperscanning. A lot of the studies show that some amount of social interaction prior to the actual exercise that you're going to do, or the say a lecture that you're going to deliver, helps increase interbrain synchrony. So there's that aspect as well, where you probably want to get the trainer and a bunch of trainees to do something like a team building exercise before actually delivering the content that you're there to deliver.
Okay, great. Yep. So any other questions?
I've just got a question for Amit.
Oh, yeah.
You talked about physiological sensors and trying to use multiple sensors.
Yes.
Also, just the concept of cognitive load that you just talked about. Can you define that a bit more, and how do you plan to integrate the different physiological sensors? Are you think you're doing a machine learning model, or are you trying to use a mathematical?
Yeah, so we have a few students. Well, we have one student or two students specifically working on the machine learning side of things, and in terms of being able to define emotion or cognitive load, there are a few what do I call them, benchmarks, or few data sets that are available that serve as ground truths. So basically, for example, we have this thing called the International Effective Picture System, which is essentially a bunch of pictures, but the entire data set has been validated in such a way that every picture has a particular valence and arousal rating that is attached to it. And so we will, for as starters, I think, go through that before trying to go into the more abstract, which is the emotion. I hope that sort of answers your question.
So what do you mean by interbrain synchrony? Do you expect the brain in the participants, do they want to be in a synchronized state, or?
Yeah, so I mean, so two things. So there is this concept of flow and connectedness. So when if you talk to people who play team sports, or say a group that's dancing together, they'll tell you on a particular day, we just knew what the other person was going to do, especially with sports people. Like you talk to someone who plays basketball or football or whatever, they just know, like, that. And the word that is constantly used is the team was in flow. So it's basically like different parts were all of a single entity, were all everything seemed like it was just one entity doing the entire thing, not a bunch of different people coming together. So there's always been this concept that we are connected in some way, but over the last, say, 15 years, because EEG headsets have gotten cheaper and better and things like that, people have started studying these concepts of interbrain synchrony, where they feel that when two people collaborate together on a task with a common goal, their neural activity tends to synchronize. So the current metrics that have been developed to assess interbrain synchrony have been criticized a little bit, because they say they're simply detecting reactions that we would expect people to have to a very similar stimulus. But then there are now people trying to develop more robust ways to actually say that, yes, this is actually interbrain synchrony that's happening, and not some spurious connections that are being detected between the brains.
Okay, that's very interesting.
Yeah.
Okay, any other questions from the audience?
Yeah, so this morning I was doing a video conference demonstration with the US of a device that we built and was sent over to them. Because of COVID-19, I can't deliver it and be there to commission and train the people. So we did it by video successfully, but your 3D rendering thing was for the whole room. My question is that if you've got, usually when you're sharing or trying to do some task focused thing, you're actually dealing with a smaller field of view or a smaller volume. So like your desk, for example, whereas, so can your 3D rendered technology be able to scale down to like essentially, not zoom in, but maybe perhaps look at a smaller working space or working area?
Yes, for sure thing. So because this cluster, of course, we can, how we design the cluster matters. For example, we can, for the robot experiment, actually we only use 2. But for our 360 3D, we use 8. And we can manipulate the shape of the cluster and the numbers of sensors to adapt different size of the application scene. Normally, we will say, you're right. So most of the work can be done on desktops, desk size, but then can move to, say, workbench, sorry, and then go to room scale. And eventually it may also, we try to also now try to explore the floor scale, say the whole ABI of level 9 could be captured as well. It highly depends on the application and the target, but it can be optimized.
I would imagine a smaller scale would be more beneficial for more of the time than a floor.
Yeah.
It's not very often I need to demonstrate something on a whole floor to somebody, whereas, you know, if you're looking at a small, I mean, I'm a mechanical engineer, so I'm always dealing with detail. And the other question relating to that is like the resolution of the some of those renderings you showed. I don't know if it's the linkage or what, the resolution, you can't make out necessarily the size of smaller components.
Yes, well, that's a hardware limitation, but these days, last month received the LiDAR sensor, which equipped with the, similar to the technology equipped with the iPad Pro. So I can give a really accurate, I believe the accuracy is around 5mm accuracy. It should be enough for the desk size of the target, which provides enough details. But the sensor we used for the demo, actually the accuracy around 1 to 2 centimeter, which might not be enough for some of the application. But there's solutions or technology that can be applied to solve the accuracy problem.
Right, okay. Mm.
There is one question from the chat box. It asks, human eye have some level of depth perception. When we see through a moving 2D 360 camera, we do get a sense of how the space is like 3D wise. Could you shed some light on what advantage does the 3D 360 camera has over 2D 360 camera? What are the scenarios that this new 3D technology will be most useful?
Thanks. That's also a really good question that we actually addressed this problem in the paper they published. So for the 360 2D, the limitation is it's 2D. So I just to show you when Johnny showed the camera, you can rotate around, but you cannot move around in 3D space. But for the 3D 360, you can actually freely, if you wear the VR headset, immerse yourself in this scene, you can freely move around in 3D space, feel like you are in this physical 3D world. But for 2D, you stuck your viewer perspective with the camera view. So if the local person who didn't move the camera, you cannot move in 3D space. So that's a big difference, especially if you want to collaborate with more spatial layout related task. For the assembling, you need to pick different components from different workbench and then assemble on the desk. That might be really hard if you just use the 2D camera, 2D 360 camera. So that's a big difference. Yeah. And of course, because you can freely move around, you don't need relies on the local person, right? 360 2D camera, you have to ask if you can rotate around. You probably need to ask the local person to, could you please move the camera close to that desk or something like that. But we have ECL Australia lab actually had a study, tried to investigate if we install the camera on top of a head with the AR headset. When we move around, we also move the 360 camera at the same time. Could that help or improve communication? So yeah, but there are lots of work on comparison of these two interfaces as well. And for the scenarios, most of these nowadays are in the industry, or as I mentioned, big machinery maintenance, installation, or the inspection that cannot be used for this. And also you want to monitor or track the big robots inside the warehouse. Possibly you also need to use this technology to give a more precise location tracking and also improve the safety in general. Hope I answered your question.
Yep, you says yes, thank you. If no more questions, then let's all thank Huidong and Amit for this fantastic presentation today. Hopefully it'll lead to a fruitful future collaboration with some of us. New collaboration will be formed after this. That'll be really great. And thank you everyone for coming. So, okay. Bye-bye.
Bye. Thanks.